Consider the following 2019 AMC 12B problem number 24, and here is a view of this problem. We are given this complex number, which is one of the roots, one of the third roots of unity, and obviously it's on the unit circle as such. And an alternative way to represent it, as you all know, would be CIS 120 degrees. I was about to say 60 degrees, but it's not. And let S denote the set of all points in the complex plane of the following form, where W is again CIS 120 degrees. And in this form, where A, B, and C are scalars, they are numbers from 0 to 1, what is the area of the set S, as A, B, and C ranges between 0 and 1. So it might be a good idea to just draw a sketch first. Remember that we have the unit circle. If this is the unit circle with 1i minus 1 minus I, the real part of a complex number, the imaginary part of a complex number here, something like that. And in that case, our number CIS 120 degrees will just fall onto the second quadrant. Let's use maybe this color. So we'll end up somewhere here. And this is exactly where W is. Obviously, this is a 120 degree angle. Because in the problem there's also a mention of W square, it makes sense to make note of that as well. W square is just W rotated another 120 degrees, so it will fall right here, W square. And notice here that they are right aligned, right? So this point here is root 3 over 2i, that point here is minus root 3 over 2i, and here is minus 1/2. Awesome. So minus 1/2 here. And obviously you might even think that there next to the A there's an invisible 1 there, and that one is over here. Alright, so before solving the problem using a vector interpretation, let me just give you a basic information about how to add two vectors and what that means. So suppose that you have a vector u here, and you have another vector v, and just to remind you, the sum of these two vectors you complete into a parallelogram, and boom, so that would be the sum. So this vector here is u plus v, and you can put an arrow on top of the vector if you wish to. But interestingly, another well-known property is that you can achieve any point inside this parallelogram by making a linear combination of these two vectors. So when you multiply a vector by a scalar like c, then you are scaling that vector. So you are either making it longer if c is this is cu, if c is greater than 1, and you are making it basically shorter if c is less than 1, and this is cu again. That makes sense. So therefore, what we can do is, after scaling them, we can apply parallelogram method again, and boom. So basically, you can achieve any point inside this parallelogram would be of the following form, if you will, if you wish, Ku plus Lv, where K and L, they are both between 0 and 1. And obviously you can go further. For instance, just for the fun of it, if I go this way, so this is 2u in a sense, then all these points can be represented in the same form, Ku plus Lv, where the scalars now is K is still between K is between 1 and 2, and L is still between 0 and 1 if you wish. But this is a very neat way to handle vector addition. So now what we will do is we will interpret these 3 points in the complex plane as vectors. So when that's the case, let's go ahead and let's include the arrows. So I want to rather represent it with this arrow, and that arrow over here, and in that sense it is just adding a linear combination of these three vectors. So what we can do first is you can add two of the vectors first, and then you can add the third one, so the third component. If you will, let's begin with these two first, bw plus cw square, and notice that b and c are ranging between 0 and 1, so everything within the parallelogram. So let's go ahead and complete it. So let me change color one more time. So when I add w and w square, and we can do it here if you wish, so w plus w square, and that's just these 2 points are just conjugates, right? So their imaginary parts will just vanish, and as a result, so you'll get minus 1/2 plus I root 3 over 2 plus minus 1/2 minus I root 3 over 2. These two terms are gone, and you'll get a minus 1. So therefore, it turns out, so if you add these two, you'll get this vector. And obviously it comes as a result of this nice parallelogram. Obviously the angles here in this picture are really nice. This is a 60-degree angle, another 60-degree angle, and so on. So it turns out any point within this parallelogram you can achieve simply by changing the coefficients b and c here. As long as you move them between 0 and 1, you can achieve any point within or inside this parallelogram. And that's pretty neat. Now next is, how do we further combine this result with this one? So now we have a complex number, any point within the parallelogram. Now what we should do is we should further add to it 1 times a, where a ranges from 0 to 1. So you can add any number, any real number from 0 to 1. It is akin to shifting it to the right between 0 and 1 units. So basically, anytime you have a point within the parallelogram here, you can shift it any amount between 0 and 1, right? So you can basically translate it by whatever amount you want between 0 and 1. The same thing for this point, and so on. So the farthest you can go would be if you try to translate this border, these two edges, and in that case, due to the nice symmetry, so this point will be carried here, that origin would be carried right here, and then this point would be carried over here, where these points are basically CIS 60 degrees now, and this one is CIS minus 60, or you can say it 300 degrees. And that's it. So we can achieve, so therefore there will be a parallel shift here, another parallel shift here. So we are shifting the whole boundary, and anything in this part is also achievable. Anything within this boundary, just using this simple definition of a vector, is also achievable, and that's it. Now all that's left is to calculate the area of this hexagon, right? It's a regular hexagon, and we can accomplish it by simply finding the area of one of its component triangles. For instance, this triangle, it has an edge 1, an equilateral triangle, which have a side length 1. Side length 1 implies the area of this triangle would be a square root 3 over 4, so 1 square root 3 over 4, so which is just root 3 over 4. So this is for the triangle, and now I need to multiply it by 6. So I find the area of the hexagon. Area of the hexagon, regular hexagon, would be simply equal to 6 times root 3 over 4, or 3/2 root 3, and that's it. This is the area of the set S, the set of all points in the complex plane that can be achieved by making a linear combination of the three vectors 1, w, and w square, the third roots of unity. And so therefore the answer is C, and we're done.